discussing we have been discussing how the signal comes from the source to the receiver, and so let me recapitulate what we have done so far first, and let me tell you what we will do today in this morning lecture. We'll look at something called the visibility function and the information content in the visibility function. And this is something that we'll get from the signal that we said that we received by the receiver. So let me recapitulate things. So we have already taken three assumptions, maybe sometimes silently. So one is that the radiation which is originated, which we are looking at, is originated on the inside sphere of a radius r. And after that, it comes freely to us. There can be radiation originating at different radius, which means that it's not the source in case of 21 centimeter at a given redshift, which contributes to the total radiation. But that you will see is rather trivial to add to the following, the formalism that we are doing. So that we'll see at some point in the lecture today. We also assume that the antenna is not sensitive to the entire hemisphere of the sky of a view. It is only sensitive to a given direction in the sky. And it follows that direction as the source rises and sets over the time of the day. It may not actually rise and set. Some of the sources remain all the time in the sky. Like, for example, if you look at the North Pole, the North Polar Star is always there in the sky. Daytime, probably you cannot see it, but it's there. But anyway, so once you decide that your phase center, as we discussed last time, is supposed to be in a certain direction in the sky, which usually you give by the right ascension and declination, RAD coordinate system, it stays there. So that's the other assumption. And once we looked at those, we arrived at the recorded voltage by the analog receiver at the antenna A. And let me just go through the terms. So I probably did not write that delta before VA. So this delta is there because we are considering that all the electric field that is originated at a source is from a small patch in the source, which we called delta R. So really, if you want to get all the radiation, you have to integrate over delta R. But nevertheless, you have the things from the right to the left, the electric field at the source, which is given here, which then propagates to the outer ionosphere. And the propagation is just given by the Huygens-like propagation. So you can get this factor directly from any Fourier optics exercise. Then it goes to the ionosphere, which adds these two effects, out of which we will neglect the effect of the time delay, which is this part today. So we can include it. Of course, it is required to include it, but just for simplicity, we'll neglect it. You can deal with it just like all the other terms that we will deal with. I will just not mention it in the following discussions. The ionospheric phase is very important for us, so that I will keep. Then it says the antenna receiving pattern. Actually, it is not only the dish, the shape of the dish that matters, but after the dish, you also have a dipole, which actually receives the signal. And it's a combination of the shape of the dish and the receiving pattern of the dipole that matters for the antenna beam pattern. Remember that this is the antenna pattern which multiplies the electric field. Usually when I call antenna pattern, I mean what multiplies the intensity. It is not that, it's what is multiplying the electric field. Intensity is like electric field square. And then at the end, we have this receiver gain. And if you look at this entire chain of the thing, you don't have any mention of frequency anywhere. And that's for a good reason. Because when the signal comes to you, you can actually record the signal as a function of time. This you can do because we are talking about a frequency, radio frequency, which is like a few gigahertz. And if the signal is few gigahertz, you can very well sample it using a computer. if the signal is like the signal for optical signal, which is like 10 to the 14 hertz, there is no computer that exists today which has a clock speed as fast as 10 to the 14 hertz, such that you can actually measure the electric field content of the optical signal. Here you can measure the electric field content, the frequency content, the time variation of the signal, which is let you measure the electric field with its phase. And that's an advantage. That let us measure the coherence of the signal. That's why the detection of the signal in radio astronomy is also called coherent detection of the signal. All right. So the electric field originated from a position capital R in the source. If you remember that R gives you any point in the sky. So in this case, the vector R was given by a unit vector n cap, which directs towards the direction of the particular position in the source. And as I said, that the source is at a distance R away always. And Xa is the position of the antenna. Now, you also see that in some cases, I have also used the suffix A, like here, or for the gain. That is because these quantities depends on the antenna that you are looking at. It may not depend on the position of the antenna, which is Xa. So Xa is one quantity that depends on where the antenna is, which antenna you are talking about. And Xa gives you where the antenna is. But there may be other things like what is the receiver that is sitting behind the antenna. That will have a particular type of gain. So I denote it by a suffix A. And if you remember, this dA is nothing but the distance between the point of source, point in the source where the electric field is originated, and the point in the receiver or point in the antenna where the electric field is received. So it's that distance essentially. Lambda is obviously the observing wavelength. Okay, so now what an obvious thing to do to get the total electric field content is to integrate this. If I integrate this, instead of delta V, I will get V. And remember that delta, that integration was essentially the integration of a given point in the source. So whatever which is a function of capital R or n cap will be integrated over. So I should put the integral here, because everything following that is a function of n cap. And then I can make it the measure of the integral. Okay, so that is the voltage that is received by your antenna. The entire source contributes, that's why the integration is being put in. So let us now look at the property of this voltage. And as I said, that we have not talked about the frequency content of the signal yet. So how to get the frequency content of the signal. So this is my voltage. Remember that this is a complex number. Most often or not, I will just talk about one property of the complex number. And if I talk about, for example, the amplitude and phase division for the complex number, then I'll talk about amplitude or phase. I may talk about the real or imaginary part. For some of these discussions, I'll really not distinguish that. I'll not really tell that I'm talking about the amplitude of the voltage or the phase of the voltage. All these mostly go, the discussions that we do will follow mostly for any of these quantities, either amplitude or phase or real or imaginary part of the signal. Now, usually when I look at such a signal, I can always see that it has two parts. One varies rather slowly, and the other one varies fast. Okay. And most often or not, I can kind of write this first variation times the slow variation, as I have written it here. So the slow variation in time just behaves like an envelope of a faster variation. So let me show you what I mean. So here is a signal. In the top panel is a signal which I have obviously fabricated in a computer, which you can see that there are several variations in this signal. There are different time dependencies. The prominent time dependence, you can see there is a very fast oscillation. And then the amplitude of that oscillation is kind of modulated by a different signal, different wave. If I just look at the slow variation that is given in the bottom part, and if I just look at the first variation that is given in the top part, what I can do is I can take a window like I have shown here and average the signal over that window. If I average the signal over this window, the fast variation will cancel out. You can try to do that. If you take the averaging window size with the averaging window size, the width of the averaging window, which has a time length much higher than the time period of these oscillations, then you will see that smaller variations will average out. And after averaging, I may write that signal down as a point, as I have done in the middle panel. And that I can do now. I can shift this window everywhere in my signal, and I can keep on pointing out what is the average value that I get. And what does it give me? It gives me the overall variation of the signal. So that is the slower variation, and the faster variation is the one which is in the bottom. So if I now take care of the faster variation, I will get the slower variation, and vice versa. Now, if you look at this signal, it is quite apparent that the faster variation here is a single frequency oscillation, which essentially means that I can say that the signal that I have plotted here has an oscillation has a sinusoidal oscillation, a monochromatic oscillation with a given frequency, and then on top of that there is a slower variation. So I can say that if I focus our attention to that the time where the box is put in, then that point in the second panel gives me kind of the mean of the signal, and the point and the oscillation in the below plot gives me the frequency content of the signal at that time. In this particular case, it's obvious that the frequency content doesn't change across the time, but it may. In a general case, you may have a signal for which the frequency content is changing with time. Now, this is a single frequency oscillation. Let me ask you, now this is a different signal. The top and the bottom panel, if you look closely, they doesn't look quite same. There is subtle differences. May I ask you that how many frequency do you think you have in this signal? Somebody please. Hello. Are the participants allowed to unmute themselves at this stage?
I think yes, they can unmute themselves.
Okay. So, so my question is that, what do you think that how many frequency you have in the signal? So the lower part, the bottom panel has only the frequency content of the signal, which is the faster oscillation. Anybody? It's a very, very well-known pattern. Okay, I'll not give you the answer. So you may try to figure out the answer yourself, and you may discuss by yourself.
Is it 3, sir?
Why 3?
So, sir, if we see the first one is the
no, I'm just talking
signal.
about, I'm talking about just the bottom pattern.
The modulated, the bottom 2, sir, 2.
Bottom 2, right? So the bottom is 2.
This is
quite evident because this just looks like what you have heard as beats, right?
Yes, sir. So one is the fast frequencies and another is the modulated on.
No, so there are 2 frequencies here which are very nearby, and that will give rise to beat, right? So you can try to. So if you add 2 frequencies which are very nearby, that will give rise to a beat like structure like this. But anyway, so the point here to make is the faster oscillation contains the frequency content of the signal, and the slower oscillation contains the overall variation. And if I just average the signal over a certain time window, I will get a value. I will not get the frequency content of the signal. I will just get the middle panel here. I'll not get any information of the bottom panel. So to get the frequency content of the signal, what I have to do is not just average, but average with a Fourier transform kernel, which is essentially this. And then you do this operation from a window. I call this, see, this is the integration is just a window, time window, which has a width of tau s. I will tell you why we call it tau s. What happens if I do that? Well, over that small time tau s, the slow part of the signal doesn't change, so that can come out of the integration. And then the rest is just the Fourier transform of the first part. So that will give me the frequency content of the signal. Okay, so once I get the frequency content, then I can now see there are variation with t also, which is a slower variation. So now I can write the same voltage as a function of time and frequency. And all the frequency content of the different parts that we discussed earlier. So wherever there is a fast oscillation in this, that will come a part of the frequency. That will give a frequency dependence of the signal. Okay, so if there is any question at this stage, please ask. Okay, so what I do is, I not only do this integration, but also, so how do I do this integration, first of all? So I don't use, so usually the radio telescope today doesn't use an op-amp to do the integration. What you have to do is to first sample the signal. What do I mean by sampling the signal? I had this continuous signal received by the analog receiver. I digitize the signal at certain time interval. So let's call that time interval delta t. So I digitize the signal at certain time interval delta t, and then I change. So once I have it in as a time interval delta t, the signal doesn't look like this anymore. It looks like ti, I for different sampling. And then this integration essentially becomes an operation of summation, right? Now, you may ask the question, what should be the value of delta t? Usually, one chooses delta t same as tau s. Delta t much smaller than tau s, obviously. But what should be the value of delta t? Now, delta t is at the time scale, at the resolution in which you are sampling your signal, and it tells, there is a theorem called Nyquist-Shannon sampling theorem. Nyquist-Shannon sampling theorem that tells you this should be less than 1 by 2 times the bandwidth of the signal that you want to measure. So let me not call it Let me call it bandwidth here. Okay, so what do I mean by that? Well, say I want to do, yeah, thank you. So Barnali corrected me with the spelling, which I am terrible at. Thank you, Barnali. So what do I mean? I mean the following. So remember that when Kanun was talking about creating the signal in a simulation box and then observing it, you are the H1 signal you will observe from different redshifts. But if I change the redshift too much, obviously the universe will evolve. So I will not be able to capture the universe at a certain stage of its evolution. So always when I observe at say 150 megahertz frequency in with a radio telescope, I have a certain bandwidth around 150 megahertz, maybe plus minus 8 megahertz. So 16 megahertz band. So if I put 16 megahertz here, now you can calculate what your delta t should be, and I leave it to you to calculate. It will be few nanoseconds. So you sample the signal at few nanoseconds, then you do this operation. Obviously, this tau s has to be larger now. And then at the end of the day, you get your voltages now digitized as a function of time and frequency. Now, let me tell you that I am following a particular path in the signal chain, which is to say that it can be done in different ways. I am following a particular way it is done in some of the radio interferometers. And this particular way is called FX way. F stands for Fourier transform, which gives you the frequency content of the signal. And X is what we will discuss now, which is correlating the signal. Okay. And Barnali corrected me again that I missed the N here. All right. So let's see that what do I do next with this signal? What I do next with this signal is to calculate this quantity. So I have now V at an antenna. Okay, so from now on, so we have known that how to get the frequency content of the signal. Again, just for simplicity, and as you have seen, the things becomes very long and doesn't fit into one line. So I'll not write the frequency explicitly. Everything depends on frequency, and for the time being, we can assume that we are dealing with only one frequency. Okay. There is something that this windowing of the signal does to the frequency content of the signal, which is that it adds a frequency dependence. Why is it so? Well, if I look at this expression, it's not quite a Fourier transform, because the Fourier transform integration is supposed to go from minus infinity to plus infinity. If I really want to write a Fourier transform, I better write it as minus infinity to plus infinity, and then a window, which is this window, and then write V, and Fourier transform kernel, etc. etc. If I really do that, then you see when you go to the Fourier domain, so this is a, so here you convolve with this window. Maybe I'm going a little bit technical. If you do not understand this part, it's all right. You convolve this with the signal, which essentially gives you an extra factor in the voltage. Okay. So when I measure this frequency content of the signal, because of this windowing, there comes something which I call the band pass. which is a frequency response of your digital circuit, which is doing all these operations. So this can be a function of both, again, frequency and time, which means that it's not that there is an oscillation with this frequency, but the number that you get to multiply with the actual voltage frequency content of the voltage varies with frequency. That's why it's a function of frequency. And it can also vary with time, depending on the characteristics of the electronics which is doing all these operations. So which essentially means then if I want to write down the frequency contents, if I now include nu or omega over here, I need to include another term here, which is this band pass, which can depend on which antenna you are doing, because all the electronics is behind the antenna, and it's a function of frequency and time both. Okay, so I'll come back to it, but let's see what we do with the signal. So, and as I said, that we will, from now on, we will, just for simplicity, we'll deal with only one frequency. So I'll not write it explicitly. Everything I write can be function of frequency. So what I do is this. I take the signal from the two different antennas and do this operation, which I call correlation. Okay. So it's obviously abstract. I really do not know what I am meaning by this bracket. What in practice you do is that, so let us call this, let us give this a name. Let's call this curly V, AB. This will depend on obviously XA, XB, T, and frequency, which I'm not writing. So what is this? This operation of correlation is nothing but a time average of the signal at voltage, the voltage signal as antenna A at time t, and the voltage signal at antenna B, not at time t, but you have, remember that the signal from the sky does not reach the two antenna at the same time, just because, so if you remember this geometry that Poonam showed you earlier, that if the antennas are looking like this from a source there, this is the equal phase plane. So the signal reaches this antenna earlier compared to that antenna. And the difference, time difference between these is what I call tau g. So that's called the delay. So I do not, because I am receiving the signal over time, I know what the time I should shift the signal before I do the correlation. So I do that. Okay. So this is what I do as the correlation. Now, may I ask the question that what should be the value of this tau? How long should I correlate? Okay. Now, this correlation is done in a particular way. If you remember the contents of this has the electric field from the sky, and then there are certain factors, all of which are usually called gains. Factor from the electric field from the sky, and after that there is a propagation factor which doesn't have any time dependence. Then you have the factors like the antenna beam pattern, the receiver gain, the ionosphere, all of these. Now, all of these varies at a much higher time scale than the signal itself, because remember the signal also has the oscillations. So what you do is you choose this tau to be much smaller than the time scale of variation of any of these quantities, but much larger than the time scale of variation of the electric field at the source. So for example, it's a monochromatic signal. The time dependence will be just e to the I omega t. And you choose tau to be much larger than the time period of the signal, which for 1 gigahertz oscillation is 10 to the minus 9 second. Right? So for example, in GMRT, this will be few tens of milliseconds. Okay, so this is what I do. Now, before I write down the full expression for VA and VB, let us understand one thing, that again, because there are different time scale oscillations, when I do this integral at a given time, over the time scale of the integral, which is tau, none of this gain term will change, or the ionospheric effects will change. So they will all come out of the integral. The real integral over time will only happen over the time dependence of the electric field at the source. Tell me if this point is clear, because this is quite crucial. If there is any doubt here. Fine. So the receiver gain antenna pattern.
I have a question.
Yeah, please.
What I understand is that we are trying to smooth out the very fast varying parts of this signal. So, is it correct?
What do you mean by whether it is correct? We are doing some operation. What will be the result of this that you will see, right?
No. The very fast oscillating part we are trying to average out, right?
I didn't say that we are trying to average out. See, when we are doing the averaging here, we are not doing any correlation. We are just taking the voltage and then doing the integral, right? Now we are multiplying the voltage which are measured at two different positions, XA and XB. So this, if you remember our earlier discussion, it's not a correlation, it's a cross correlation, right? I am correlating the voltage from one antenna with the voltage from other antenna. It's not really, it's an averaging over time, but it's not a smoothing effect that we were discussing earlier.
Okay.
Okay, what is the result of this? Obviously, that is what we will see next, right? Okay, now the point I made.
Prasun, I think Sonia has a question. So Sonia, you can unmute yourself and.
Yeah, please go ahead. Hello. Or you can also, if you cannot.
Yeah, you can type in the chat.
You can also write in the chat box. I am looking at the chat box in some interval and will give you the answer. Try to give you the answer. Okay, so as we said, that the integral will only evolve on the electric field part. So let us shift the integral to the electric field part and see what we get. So let's calculate this quantity, which I call CAB. Okay, so there is one more point which I realized after writing this down. When I evolve the integral inside only this, and then there will be another E from the other antenna. you see that
So, Prasun,
there will be,
Sonia had this question.
I will get to that. I'm looking at this at the questions. I will get to that. Okay, so I will have this integral over r, which is a particular direction in the source, but you are really integrating v two times separately. So the integral variables should be different. So which means when I write this I should write as 1 by tau t minus tau by 2 to t plus tau by 2 dt prime. And now E star, which originated from R, the signal was earlier at an earlier time, and remember the integral variables is supposed to be different. This is received by the antenna B, so I should write dB here because dA is the difference between the position in the sky and the antenna, and I should add up tau g, which probably will be a plus. Okay, so let us ask the question. So this is what I will get once I shift the integral only to the electric field. So let's take the question from Sonia, and by then, if you have any further question, you can ask. Okay, so two of you have asked that how do I choose the value of tau? See, what I want to do here is to keep a certain frequency oscillation in my signal. Okay. Now, okay, let me see. See, now, if I am observing at 1 gigahertz, I really don't need to sample the signal at 1 gigahertz. So if I just try to draw a frequency line here and some amplitude of the signal, if you wish, in the y-axis, and say I want to observe at say 1 gigahertz, which is there, and over a small window over there. Okay. What is done in a radio interferometer is there are intermediate steps which I have skipped. And one of those steps is to add an intermediate frequency signal. And you know that if there is a band limited signal, the frequency content of the signal in that band can be shifted to other part of the band. So that is done. And this is transferred. So this was say in 1 gigahertz minus something to 1 gigahertz plus something, which is now transferred from 0 to the bandwidth of the signal. Okay. So now the highest frequency signal that I want to see, want to observe, is just the bandwidth of the signal. Okay. So imagine that you have 1 gigahertz minus 16 megahertz to 1 gigahertz plus 16 megahertz you wanted to see. But that 1 gigahertz minus 16 megahertz now is shifted to 0, and 1 gigahertz plus 16 megahertz is at 32 megahertz. So my bandwidth is now just 32 megahertz, and your Nyquist-Shannon sampling theorem will tell you that you have to sample it at twice the frequency of the signal, right? So that is what is done, and this the shape of this filter is called the bandpass filter, which is what I was writing as b omega t. I did not want to go into this detail unless you had a question, but now you can. Does that answer your question? You can say yes, no. Or if you have, we can take up that at the end of the lecture, maybe. For the time being, you can assume that you sample at this, and the sampling also gives you this bandpass response. All right.
Are
Yeah.
they choosing antenna positions according to us?
Yeah,
A
yeah.
and B.
So how you so about the antenna positions we'll discuss when we'll go to imaging. Okay, maybe in the next lecture if you have time, maybe tomorrow morning. Fine. For the time being, you just assume that for the all the discussions here, you can just assume there are two antennas at two different positions, XA and XB, and you can assume there are many of them. Every pair, you are taking the voltage from every pair and doing this correlation operation. All right.
Yes.
Okay. So what do we get here? Let's see. Well, if you this is a remember that we are talking about a monochromatic signal. There is a little bit difficulty at this stage. We are talking about a monochromatic signal. We said that we will deal with only one frequency. Now, if it is a monochromatic signal, what is dB minus dA by C? dB is the distance the signal travels from the source to the antenna B, and dA is the distance the signal travels from the source to the antenna A. So dB minus dA by C is nothing but the time delay, right? That's excess distance traveled divided by the speed of light at which the signal travels. So in that case, this dB minus dA by C, I can just write for dB minus dA by C as tau g. And this will then just become A tilde R prime T minus dA by C. Right? So now, if it is not a monochromatic signal, let me just tell you and not discuss right now that inverse of this has to be much larger than the bandwidth of the signal. Again. And we can discuss that later, why that is required for a non-monochromatic signal. But if it is a monochromatic signal, there is absolutely no problem. I just get, so I can just replace this, whatever is here, I can remove it and replace it with this. Okay. So what is this? So basically now what you are doing is you are again doing a cross correlation of the signal originated from 2 points in the source at the same time, right? The time is should be T prime again. So at the same time, the two signals are originated from two different parts of the source. Now let's ask the question, is it possible that these two signals are coherent? When will I have a coherent signal? I will have a coherent signal when there is a cause which gives you the effect at these two different points in the source R and R prime, and the effect then can give you a coherent signal. So what is the distance between R and R prime? Let's ask the question, what is the minimum distance that you can expect? Well, if you consider a radio interferometer, the minimum distance I can think of as what I can resolve in the sky. Like for example, so this R and R prime, remember that R is R times n cap, and R prime is also R times n prime cap. So it's really two different directions in the sky. So if I have one antenna here, this is one direction it is looking at, this is another direction it is looking at. If these two directions are smaller than the resolution of the telescope, obviously I'll not be able to distinguish them. That's the meaning of resolution. So for a typical interferometer, the resolution, okay, so let's talk about the best interferometer that you can make on the surface of the Earth. So say 1 microsecond. Okay, I am really optimistic here. GMRT goes to 1 second, 10 to the 6 times this. One second is approximately 10 to the minus 5 radian. So this is, sorry, 1 second is approximately 10 to the minus 5 radian, yes. So this is 10 to the minus 11 radian. And the distance to the sky when you are considering all the cases, all the practical purposes, they are 1 megaparsec or above, right? So if I really ask the question, what is the distance here between the 2 points in the source? 1 megaparsec is how much? 10 to the 22 meter. So you can see the distance, if you just do the arc times, arc is the angle times the radius, you get a distance of the order of 10 to the 10 meter. I mean, maybe a little bit off. Even light will take quite some time, quite 100 seconds to go from one part to the other. There's no way you can have a cause which is at a given time, or even if you take a very small time interval, there's no way that something will influence, same thing will influence 2 points in the source. So which essentially is telling you the electric fields here and the electric fields here in the source should not be coherent. Well, I said coherent. And if you look at these, they're done at the same time at 2 different points of the electric fields originating from a source. So it's the electric field of the source. This is nothing but the autocorrelation function of the electric field at the source at a given time, right? And if there is no coherence, we saw last time what should be the autocorrelation function. It's just a delta function at some r, right? So this quantity CAB once I do the autocorrelation, there's no coherence between the electric fields originated at r and r prime. So this can just be one particular thing at whether you call it at r or r prime, and then a delta function. So this I can write as delta r minus r prime. Just let me check my notes once to make the dimensions correct. If you have any question in between, you can go ahead and ask. So I will write this in this way. R is same for both of them. So I introduce the intensity here. Okay, so this is essentially the electric fields. Okay, so you have any question? Can go ahead and ask, otherwise we'll proceed. Okay, so let us proceed then. So I get this, right? So now I can use this. And if I want to do the correlation of the voltages, I have to carry all the other terms also. And remember that I said that I will not bother about this term for this lecture, the delay that the ionosphere introduces. Other than that, I have to carry all the terms. I have no other option. So let us write that down now. So we are calculating this quantity, or let's see. So we are calculating this quantity. So I'll just write that, which is the correlation of the voltages from the 2 different antennas. Again, let me remind you that I'm not writing the time dependence, frequency dependence explicitly. I remember I have a 2 pi by lambda factor, which let us include in my gain. So this the band pass, the 2 pi by lambda factor I include in this. Then I have to write the same thing from the other antenna. I have the integration over dr and dr prime, which I write as integration over n and n prime. And so remember that dr is n cap r square, dn cap r square. So I'll get 2 of these r square outside, r to the power 4. Then I have the phases introduced by the ionosphere, if you remember. Where are those? So this phase is introduced by the ionosphere. So let us write those down. This depends on all these quantities. Minus sign because I have to take the complex conjugate of the antenna contribution for the antenna A. Then I have this. And finally, I have the delta function contribution. So this is the integral that I really needed to do for doing the time correlation. 1 by r square, which comes here. Okay, so what all I have done is I have just collected all the term and written it down. I have not done much in this particular case yet. So let's do some approximation. See, I have this quantity dA in the denominator, dA and dB. Okay, so let's first do the integral, which I can do now because I have a delta function sitting over here and I have integral over n prime. So I can do the integral, and I will not like to write it down again. So what I will do is, everybody knows what is the effect of a delta function integral, right? So what it will do is, it will change all n prime to n. So let me just remove this, and I will have place to write that down. So I n prime here, and all the prime becomes n. That's it. Now, if you look at dA and dB, so what are they? So dA is, let's say dA square is r minus xa mod square, and dB square is r minus xb mod square. Well, because they are both in the denominator and R is much, much greater than XA, both of these I can write as R square. R is the distance, again, few megaparsecs, 10 to the 22 meters. XA is of the order of 10 to the 5 meters. I don't think that we should shout if I do this approximation. So which means I can now remove this dA and dB from here because both of them has just become R. And I will get 1 by R square here and another additional 1 by R square, both from dA and dB. So this also gets removed. Simplify that. For the time being, let us assume that these does not depend on which antenna you are looking at. And I have already not written the time dependence. We'll put back those dependencies later. So for the time being, let us say that the antenna beam pattern is exactly same for all antennas. So then this just becomes a n cap. Now this A is something that multiplies the intensity. So this A is this quantity. When the beam pattern is same for both the antennas. Okay. What is left for us to calculate is this, particularly the phase. And the phase here has this dA minus dB. And we need to be a little careful here because it's the phase. So if you calculate this, I'm not doing it here. You will see what you will get is XB minus XA by, okay, so XB minus XA, and then you have this 1 by lambda over here, dot n cap. Okay, please try to do this calculation. So you have to just expand these and keep the relevant terms. This quantity, which is the difference in the position of the two antennas in the units of the observing wavelength, is one of the very important terminology in radio interferometry. This is called the baseline. Okay. Now this is a vector. I can take the vector I can choose a coordinate system to write down the components of the vector. If I write down the components in the coordinate system that we have already chosen, which is in the coordinate system where the n cap unit vector is L, M, and N. Remember that L squared plus M squared plus N squared is 1. In that coordinate system, I call the components of U as U, V, and W. Okay. This is the usual nomenclature that is used in radio astronomy. So with this, let's see what we have got. We have got this quantity which are these two. I have now separated them out in terms of what are their contributions. One is bandpass, one is gain. I have the ionospheric factors, which let me write this as D. It's just a name for that e to the power whatever you have as the ionospheric factor. This is not curly A anymore. Curly A was that is for an antenna. Now this is which is multiplying the intensity. Okay. So let me just level these terms and then I will stop bothering you for the time being. So this is the band pass response of the electronics. This is the gain, receiver gain. These are ionosphere. Antenna. This is the source intensity. And so one term I have not written yet is the noise, which will inevitably be there because you are dealing with an electronics, which can change with the baseline, the time, and the frequency, which I am not writing. Okay, so this is not quite what you call the Van Sitter-Janicke theorem. Actually, if I consider all the gain terms, so what is a gain term? A gain term is something that depends on the antenna, frequency, and time. Those are all gain terms. So bandpass is a gain term, receiver gain is a gain term, ionospheric gain is a gain term. And the way I have written the ionospheric gain here is different from the bandpass and receiver gain, because bandpass and receiver gain is outside the integral. They doesn't depend on the direction in the sky. The ionospheric gain here, as it is written, depends on the direction in the sky. So this part here is a direction dependent gain, and these are direction independent gains. Because they're direction dependent, that's why I use small d over here. So if I choose all these gain terms to be 1, what you get is a Van Sitter-Janicke theorem, so which we'll discuss in the next lecture. So I'll stop here now. Questions?
So we can have 1 or 2 very quick questions.
Yeah. So Bernoulli had a point, which is dA and dB will also contribution and GA and GB. That is true, that we will see. Again, we'll break down the contribution in the gain of different time scales. Okay. And we'll see that some part of the ionosphere also will not depend on the direction you are looking at. So that can go out of the integral. Yeah, other questions, please.